In this video, we're going to be taking a look at some examples of computing arc lengths of smooth curves in the plane. In particular, we're going to be focusing on curves that have an equation of the form y equal f of x. So these curves will be functions of the variable x. Recall that the length of a smooth curve, y equal f of x, along a closed interval from a to b is given by the following integral formula. The arc length will be the definite integral from a to b, which are the endpoints of our interval, of the square root of 1 plus the derivative of f squared, dx. There are two integrals shown here using different notations for the derivative, and depending on the type of function that we have and the way the function is presented, one of these two forms, either f prime of x or dy dx, might be more applicable to use. The goal of any arc length computation is to simplify the integrand of this integral in such a way that this integral is easily computed. And so what we'd want to do once we have our function f of x is to compute this integrand by first differentiating it, then squaring it, adding 1, and then taking the square root. And depending on the form of the expression, sometimes the square root simplifies completely. You might have a square root of a perfect square, for example. And sometimes we're able to factor something out of the square root and then use a substitution in order to compute the integral. But the actual evaluation process and simplification process is determined heavily by the function f of x and the form that it takes. In our first example, we're asked to find the arc length of the curve y equal 2x to the 3/2 power plus 1 along the interval 0 to 1. So in order to do this, we first find the derivative of our function. So here we would have dy dx, and this would be 2 times the derivative of x to the 3/2, which will be 3/2 times x to the 1/2, according to the power rule. And the derivative of the constant plus 1 is 0. And of course, here the 2's will cancel, and we simply get 3 times x to the 1/2 power. Once we have the derivative, the next part of the arc length formula is to square that quantity. So we're going to take dy dx and square it. And here that means we have 3x to the 1/2 power squared. And this evaluates to 9x. We have 3 squared is 9. And x to the 1/2 power squared would be just simply x to the first power, or x. The arc length formula is then 1 plus this quantity inside the square root. And so the integrand of our function will be the square root of 1 plus 9x. And so the length of our curve will be the definite integral from 0 to 1, the interval on which the arc length is to be considered, of the square root of 1 plus 9x. And now we just need to evaluate this integral in order to find the length of our curve. So in order to compute the integral from 0 to 1 of the square root of 1 plus 9x dx, we can make a quick substitution where u is 1 plus 9x. du would then be 9 dx, the derivative of 1 plus 9x. And since we simply have dx in our original integral, we're going to look at du over 9 as dx and make that substitution. So here we're going to have the integral from 0 to 1, and we want to be careful. Those are values of x, not for u, so we will want to go back to x before evaluating at our limits, of the square root of u times du over 9. We can bring the 1/9 outside of our integral, rewrite the square root of u as u to the 1/2 so that we can use the power rule. And now this is a relatively straightforward integral to compute. We're going to get 1/9 times 2/3 u to the 3/2, and that's going to be evaluated from x equals 0 to x equals 1. So we get a constant of 2/27 in front, multiplied by u to the 3/2, and u is going to be 1 plus 9x. So we have 1 plus 9x to the 3/2 power. And now we're set to evaluate at 0 and 1 since we've returned to our variable x. When we substitute in 1 to this expression, we get 2/27 times 10 to the 3 halves power. And there's really no nice way to simplify that. And when we substitute in 0 for x, we do need to be careful because we do have this plus 1 here. We get 1 plus 0 to the 3 halves, and that is going to be 1. And so our arc length, the length of our curve from 0 to 1, will be 2/27 times the quantity 10 to the 3 halves minus 1. If you'd like to try a similar example, pause the video and find the arc length of the curve y equal 4/3 x to the 3 halves power plus 2 along the interval 0 to 1. You can resume the video, and in a few seconds, the full solution will appear. The first step of this example is to find the quantity square root of 1 plus the derivative squared. To do that, we first find the derivative by using the power rule, and we get 2 times x to the 1/2 power. We square that to get a quantity of 4x, and then substituting that for the derivative squared inside the square root, we end up with an integrand of square root of 1 plus 4x. So our arc length, the length of our curve from 0 to 1, is given by the definite integral from 0 to 1 of the square root of 1 plus 4x dx. To evaluate this integral, we can use a quick u substitution with u equals 1 plus 4x, and therefore du would be the derivative of that expression, or 4 dx, and therefore du over 4 will be equal to dx. We can substitute these expressions into our integrand, and we end up with 1/4 times the integral from 0 to 1 of u to the 1/2 power du. We find an antiderivative for u to the 1/2, which is 2/3 u to the 3 halves. We combine our constants and substitute 1 plus 4x back in for u, and evaluate from 0 to 1 using the fundamental theorem of calculus, and our resulting arc length is 1/6 times the quantity 5 to the 3 halves minus 1. In this example, we want to find the length of the curve of f of x equals x cubed over 12 plus 1 over x along the closed interval 1 to 4. To do this, we're going to use the standard arc length formula, and we need to first find and evaluate the square root of 1 plus the derivative of our curve squared. In order to do that, we're going to follow the algebra, starting with taking the derivative of our function. So our first step here will be to compute f prime of x, the derivative of x cubed over 12 plus 1 over x. Now, in order to do this, we want to remember that 1 over x can be thought of as x to the negative first power, and therefore, when differentiating, this will be we will get the derivative negative x to the negative second power, which we can think of as negative 1 over x squared. And so in our calculation, to kind of keep it smooth, we're going to go ahead and replace the derivative of 1 over x with negative 1 over x squared. But this side calculation is how that is going to be computed. And so going back to our function, we have x cubed over 12. The derivative of that will, of course, be 3x squared over 12, which we'll simplify in a moment. And to this, we're going to add the derivative of 1 over x, which is negative 1 over x squared, as we've just seen. And so we can clean this up a little bit, and our derivative of f prime of x will be x squared over 4 minus 1 over x squared. So we have this nice expression here, nice clean expression for f prime of x. The next step is to square the derivative of f. And so we want to square this expression that we just found, x squared over 4 minus 1 over x squared. So this means we want to compute this product, x squared over 4 minus 1 over x squared times itself, x squared over 4 minus 1 over x squared. And we're going to get some simplification here when we do this, when we expand it out. So we're going to get x squared over 4 times x squared over 4, which is going to be x to the 4th over 16. We're going to get x squared over 4 times negative 1 over x squared, which will give us just simply negative 1/4. We'll have negative 1 over x squared times x squared over 4, which will be another negative 1/4. And negative 1 over x squared times negative 1 over x squared will give us a positive 1 over x to the 4th. And so we can combine the middle terms here. They're both constants. And so we get x to the 4th over 16 minus 1/2 plus 1 over x to the 4th. And so this will be a nice clean expression for the derivative of f squared. Notice that we do have this negative 1/2 term in the middle, and it actually is going to make the most sense to keep the terms in this order. In particular, we want to keep that negative 1/2 in the middle, and it'll make our life a little bit easier in just a step or two. So in keeping with our goal to find the square root of 1 plus the derivative squared, the next step is to add 1 to our derivative squared. So we want to compute 1 plus f prime of x squared, which means we want to add 1 to this expression, x to the 4th over 16 minus 1/2 plus 1 over x to the 4th. And adding 1 here is an incredibly easy thing to do. We're going to combine our constant 1 and our negative 1/2, and adding 1 then makes this plus 1/2. And it does not change either of our terms involving x. So 1 plus f prime of x squared will be x to the 4th over 16 plus 1/2 plus 1 over x to the 4th. Now, we can actually go ahead and factor this expression. It's actually a perfect square. And we can check quickly that this is going to be x squared over 4 plus 1 over x squared, quantity squared. This is pretty easy to see because we've seen earlier what happens if we have this expression with a subtraction squared. And if we did that, we actually obtain our first derivative squared. That's where the x to the 4th over 16 minus 1/2 plus 1 over x to the 4th came from previously. And so if we just change that negative to a positive, which is done by adding 1 to the expression, then the factorization is virtually the same. We just now have a positive sign here instead of a negative sign. Well, once we have 1 plus f prime of x squared being a perfect square, then we're actually absolutely set for our integral, because the integrand of our function is the square root of this expression, 1 plus f prime of x squared. And so the expression that we're going to be integrating is the square root of x squared plus 4, x squared over 4 plus 1 over x squared, quantity squared. And of course, the square root of a quantity squared just leaves that quantity itself. And so the integral that we're going to be computing is going to be the integral of this expression, x squared over 4 plus 1 over x squared. So now we're ready to compute the arc length of our curve. We know that the arc length is going to be the definite integral from 1 to 4 of the square root of 1 plus f prime of x squared dx. And we've just computed this square root quantity. The square root of 1 plus the derivative squared is going to be x squared over 4 plus 1 over x squared. And so we simply have to find an antiderivative for this function, which we can do with the power rule, and then evaluate from 1 to 4. So our antiderivative here will be x cubed over 12 minus 1 over x. And we want to evaluate that from 1 to 4. Both of those antiderivatives are just using the power rule. In the second term here, the 1 over x squared, we are thinking of 1 over x squared as x to the negative 2. And therefore, when antidifferentiating, we're going to get x to the negative 1 divided by negative 1, or negative 1 over x, which is what we have in our antiderivative here. And we're just left with some evaluation. And so when we evaluate this at 4, we're going to get 64 over 12 minus 1 over 4. And we're going to subtract from that what we get when we substitute in 1, which would be 1/12 minus 1. And This all simplifies, and when we combine like terms and find common denominators and all of that, we get an exact answer of 6 units. And so the length of this particular curve from 1 to 4 is exactly 6 units. If you'd like to try a similar example, you can pause the video and find the length of the curve f of x equals x cubed over 3 plus 1 over 4x along the interval 1 to 3. Resume the video, and in a few seconds, the full solution will appear. The derivative of our curve f of x is going to be f prime of x equal x squared minus 1 over 4x squared. We can square that expression and obtain x to the 4th minus 1/2 plus 1 over 16 x to the 4th when all is simplified. When we add 1 to this expression, it simply changes the negative 1/2 to positive 1/2 when we combine our constants together. And that expression factors as a perfect square, namely x squared plus 1 over 4x squared, quantity squared. We then take the square root of that expression, and because we're taking the square root of a perfect square, those operations cancel out with each other, and we're left with an integrand of x squared plus 1 over 4x squared. And we're now going to integrate this from 1 to 3 to find the arc length of our curve. So we find an antiderivative of our integrand, x squared plus 1 over 4x squared, which will be x cubed over 3 minus 1 over 4x, and evaluating from 3 to 1 and combining all of the values that we obtain there, we have a final length of the curve of 53 over 6. And so our arc length for this particular curve along the interval 1 to 3 will be 53 sixths.